Hi, and welcome back to the YouTube video lecture series. This particular lecture is on the first couple of sections of chapter 2 in our book. The whole chapter 2 is about kind of what we know about atoms and molecules and how we got to what we know. From a historical perspective, the earliest ideas were put forth by the ancient Greeks, and Democritus was one of the earliest philosophers to posture some ideas about what makes up matter. And his idea was basically just a philosophical idea of a base unit called an atom. One of his quotes that I find kind of interesting is that nothing exists except atoms and empty space. Everything else is opinion. It took a while for these ideas to become more robust, and we usually next mention the name John Dalton. In England in 1808, he kind of synthesized some of the experiments that were going on, that had been going on for the last 20 or 30 years, into his atomic theory. And his atomic theory basically has 4 main points that can be pretty quickly summarized. All elements are made of atoms. Atoms are invisible and indivisible. Atoms of the same element are identical, especially in terms of mass, but also properties. Kind of the corollary to that is that atoms of different elements are not similar. And when 2 or more elements chemically combine, they form a compound in simple ratios. And any reactions involving elements or compounds don't change the atoms themselves, they merely rearrange them. And this was really a pretty monumental change in thinking. Just to illustrate a couple of these points, they're forming a new compound, and it's not that compound if it's not the same ratio throughout. So in this particular compound, it's a 2-to-1 ratio. That's an extension of a previously postured idea, the law of definite proportions, that's put forth by Joseph Proust. And it also supports the idea of the law of multiple proportions, and that is that if you have a set mass of element A, element B that forms a compound with element A, there may be more than one ratio going on, but if you have a set mass of element A, any masses of element B that are joining with it are going to be multiples of some base number. And the last point is probably another way of saying a law that you've heard of before, the law of conservation of mass. Nothing can be destroyed when elements react or compounds react. Okay, so then once Dalton kind of extrapolated some of these ideas, the idea that the atom was the base unit and there was some experimental evidence to support that, we wanted to find out a lot more about atoms. So in the 1850s, a number of experiments started to kind of answer those basic questions. What is this atom? Is it composed of smaller particles? What are the properties of it? How do atoms interact? And what does this have to do with radiation and electricity? Because if you think about it, electricity was a relatively new phenomenon, and radiation was a little bit, was in its infancy as well. So one popular experimental device was called the cathode ray tube. And the first picture I have here is a scientist who's often overlooked. This is William Crookes's cathode ray tube. And some of his early experiments showed that electrons have mass, and that was shown by the fact that a stream of electrons, which is what a cathode ray produces, was able to turn a little paddle wheel inside of this glass tube. I may have skipped ahead a little bit here, but they hadn't actually been calling these subatomic particles electrons yet, so I've jumped ahead a little bit. Basically, all we knew at this point was that there's, in these cathode ray tubes, which are evacuated glass tubes hooked up to a power source, plates, cathodes were able to generate electrons, and you could see a stream of electrons moving through the cathode ray tube due to a phosphorescent coating on the glass. Probably the most familiar name associated with the cathode ray tube experiments is Thomson. Thomson's experiments, he did a whole bunch of them, but just to show the setup for one important one, there's our cathode ray tube. As I mentioned, there's a cathode where the stream of electrons is generated, and they travel through the tube to an anode. But as soon as Thomson put a magnet up against the cathode ray tube, the beam of electrons would interact with that magnet. And in this picture, someone is holding the positive end of the magnet up against the cathode ray tube, and the electrons are attracted to that positive terminal of the magnet. That proved, or at least put forth the hypothesis that electrons are negatively charged particles. And by varying the strengths of the magnetic field and also electrical fields and studying those cathode ray tubes, Thomson he discovered a charge to mass ratio. So he wasn't really sure what these electrons really were like, but he knew that there's a charge associated with them that could be quantified in a relative manner. Numbers not really that important, but if we now determine either the exact charge or the exact mass, then a scientist could easily determine the other. So enter Millikan. This was kind of a challenge for the scientists of the time. Who's going to be able to find either the mass or the charge of this particle that we're now calling electrons? So Millikan devised a really ingenious experiment, and there's a little video here that I'll kind of talk through as it plays. But in Millikan's oil drop experiment, he set out to measure the exact charge of the electron. And so what he did was he had these two plates, and the plates that are kind of copper in color on this video were charged. You can see the top one has a positive charge, the bottom one has a negative charge. And then he took an atomizer, which is this blue bulb on the right of your picture, and injected a fine mist of oil droplets into this chamber. That X-ray machine that was just up there imparted a charge on those oil droplets. And what he did was adjust the voltage on these plates to make the magnetic field stronger or weaker. And once he made that top plate a strong enough positive charge, some of those oil droplets were, instead of going down due to the force of gravity, reversed direction and went back up due to that electrical magnetic attraction. So that oil droplet has a negative charge due to the radiation that was imparted to it by the X-ray. That negative charge is made up of electrons. And so he was able to quantify that relationship between how much field he put on those plates and the exact charge of a single electron. So just a couple takeaway points from this Millikan experiment. He determined that the charge imparted on those droplets must be from a whole number of electrons, not a fractional number. And due to not every particle had just one electron associated with it. Most of them had more than that. But the ratio, the Coulomb to gram ratio of shown in the every oil drop had a Coulomb to gram ratio that reduced to a charge of 1.6 times 10 to the 19th coulombs. So that ended up being the measured value of the charge on an electron. And so just then by using Thomson's ratio, we were able to determine fairly accurately at this point the mass of an electron. So more questions came up. What else is in the atom besides these electrons? We knew at this point that atoms had a neutral charge overall. It was not a negatively charged particle. And so that meant there had to be some sort of positive charge in the atom. And since the mass of the electron was so small, The common thought was that, well, the positive charge must take up most of the volume of the electron, and it would be distributed fairly evenly. At the same time, there's lots of studies into radioactivity, and they proved to generate great tools for studying atomic structure. We're still in the late 1800s here, so really before any modern computing. But just very careful experimentation allowed for the discovery of radiation, alpha particles, beta particles, and gamma rays. And Ernest Rutherford in the early 1900s directed a beam of these alpha particles, which are massive. They're about the size, or they're about the mass of 4 hydrogen atoms. Directed these alpha particles at a thin piece of gold foil. And if that gold foil were made of atoms that had kind of solid positive and positive charge distributed throughout the atom with very little empty space, probably a lot of those alpha particles would have just bounced off. But it turned out that most of those particles went right through the foil undeflected. And about 1 in every 20,000 were deflected, and a few bounced back like a tennis ball against a brick wall. So Rutherford built a model based on these results, and he proposed that the atom is mostly empty space, and it has a tiny central core called the nucleus. And also, to brag a little bit about my Denver Broncos, my favorite team, if you were to blow up an atom to the size of a big sports stadium like Invesco Field in Denver, the size of the nucleus would be just a basketball inside of this major venue that can seat thousands of people. So yeah, imagine your atoms as stadiums, and the nucleus of the atom is only a manageably sized ball. Okay, so let's summarize what we've learned so far. These experiments showed that there are electrons and protons. I haven't talked too much about neutrons. They were discovered a little bit later. But to summarize everything, the masses of the protons and neutrons are very similar, and they're about 3 orders of magnitude greater than the mass of the electron. So the mass of the electron is very, very small. In terms of charge, our electrons are negative, our protons are positive, and our neutrons are neutral. So now we know what makes up an atom. And there's one part of Dalton's atomic theory that proved not to be correct, and that is that every atom of a given element is exactly the same. It turns out that for a number of elements, most elements, there are varying isotopes. And isotopes are atoms of the same element, but they have slightly different masses. So just a couple quick vocabulary terms. Atomic number is the number of protons in the atom's nucleus. The mass number is the number of protons and the number of neutrons in an atom's nucleus. And it's really the protons that drive the character of an element. And if the number of protons changes, you no longer have the element you had before. But what makes isotopes different of the same element are the presence of differing numbers of neutrons. So an isotope is atoms with identical atomic numbers but different mass numbers. And the way we write this is that there's a number of ways to do it. First way shown here is where it says carbon-12. 12 is the mass number for carbon. And then another common way is to show the mass number as a superscript, and the atomic number is a subscript to the left of the chemical symbol. In this case, a big C for carbon. And you can calculate the number of, the number of protons and electrons that is equal to the atomic number, so 6 in this case. And you can calculate by the difference between the atomic number and the mass number the number of neutrons, which in this case is also 6. If we had carbon-14, on the other hand, that means that this isotope has 2 more neutrons than carbon-12 did. 14 minus 6, the mass number minus the number of protons, the atomic number, gives us 8 neutrons.